Okay, hello everyone. Let's start our first lesson on Chapter 3, Polynomial Functions. So let's get right into it right here. Characteristics of polynomial functions. So have a read through that. Those are the various definitions of a polynomial function. Importantly, it has this form, okay? And then pay attention to these. So a lot of this is actually review from Math 10C way back in grade 10. Okay, let's do a quick exercise here. Which of the following are polynomial functions? I'm going to say yes or no to each of these. This one, no, because I have a negative exponent there. Remember, this can be written as x to the negative 1. It needs to be a whole number exponent. Okay, so that's no. Likewise, this one, no, because of the radical. That's a 1/2 exponent that is also not a whole number. This one is yes, because remember we could do this. 0 is a whole number, so that is a function, polynomial function. This one, yes, okay, whole number exponents, good. This one, no, we have a fractional exponent. This one, yes, this is just written in vertex form, okay, so this has a whole number exponent. This one, yes, tricky, but if you separate it, the coefficient is square root of 5. The variable is x, and it has an exponent of 1. Okay, this one is yes. I know there's a square root, but if you reduce that, simplify it, sorry, that's x to the third minus 7. So that is definitely a polynomial. This one, no, because this is an absolute value function. Let me make this neater. Absolute value function. So by definition, just by it being an absolute value function, it cannot be a polynomial. Okay? State the degree of the polynomial, so degree, leading coefficient, and the constant term. Degree. So remember, degree is the highest exponent of the individual term. So right there, x to the 4th, degree 4. Leading coefficient, look at the highest degree term and write down the leading coefficient or the coefficient attached to that highest degree term. Well, that's negative 2. Constant term doesn't have a variable next to it. There you go, 4. This one, degree 5. My leading coefficient's 10. Constant term, there is none, or you can just say 0. Okay. This one, a little trickier, right? If I take this x and I square it, so that's x squared, and I have another x squared here, well, that's x to the 4th, so that's a 4th degree term. Leading coefficient, so I'm just paying attention to this term here now. So that 3, so that's 3, I'm squaring it, so that's 3 squared. And then I multiply by that 5, and then I multiply by the 2. So that's 9 times 5 times 2, that is 90. Okay, constant term. So I'm just going to clean this up a little bit. Constant term. I have this negative 1, and I'm squaring it, right? So I'm squaring it. I have this positive 1, and then I have this positive 2. What do I get? That's 1 times 2, and that equals 2. So your constant term is 2. Okay, the following properties affect the graphs of a polynomial function. The degree, the sign of the leading coefficient, and the end behavior of the graph. We'll talk about what this end behavior is. Okay, the end behavior of a polynomial function is the behavior of y values as the x values increase or decrease. So it's the left and right ends of a graph. So we'll look at that in a couple of examples coming up. Okay, let's go through some pictorial examples, types of polynomial functions. So a constant function where the degree is 0. So this one, y equals 3. Why is the degree 0? Because if I put an x there, that exponent on the x has to be 0. Well, we know that becomes 1. So it's essentially just y equals 3. So that's a constant function. That is a horizontal line. Linear function, this is an oblique line. That's the fancy term for, hey, it's slanted. Okay, it's not horizontal, it's not vertical, it's oblique. Okay, and then the characteristic here, it either has a positive or can have a negative slope. Quadratic function, this is what you did an entire course on in 20-1. So it's a parabola. It either opens up or down, and it is a degree 2. So as in that example there. Cubic function, this is something that's new for this unit. So it has a nice little S shape. There's some characteristics that we'll get into, but what's the thing about a cubic function? Look at the lead coefficient. Sorry, look at the degree of the lead term. It's a cubic, so the degree is 3. Quartic function, degree is 4, so you'll see that right here in the polynomial, x to the 4th. And then a quintic function, degree is 5. And then these shapes get weirder and weirder. I think of a cubic function as a sideways S. I think of a quartic function as sort of a weird looking W shape. And then this quintic function is just all over the place. Okay, it's like a peaks and valleys kind of thing. So degree of 5, and there it shows up in the polynomial there. Okay, example 1. Let's go through a couple examples on getting familiar with polynomial functions and what they look like. Consider the polynomial function f of x equals negative x cubed minus 3x squared plus 6x plus 8. Use a graphing calculator to sketch the graph and label the x-intercepts. So you use your graphing calculator. I'm going to use Desmos graphing calculator. So I'm going to open my graphing calculator. So let's type in y equals negative x cubed, okay, minus 3x squared plus 6x plus 8. So you can do the same on your graphing calculator. I just like to use Desmos. It shows you a better looking graph. So there we have y equals negative x cubed minus 3x squared plus 6x plus 8. Okay, let me do that. Let's put that keyboard away. Okay, so we have a good view of what it looks like. So go ahead and sketch it on your graph. Looks like I have a 0 at, if you do this on your calculator, there's negative 4, 0, negative 1, 0, and 2, 0. That's the great thing about Desmos. It shows you the key points. I have a y-intercept of 0, 8. So I'm going to go back to my graph here, sketch it. Let's plot those negative 4, negative 1. Okay, and then I have 2 here. So let's just sketch. Doesn't need to be perfect, but get some accurate points in there. Okay, I'm just going to go back to Desmos. What was that y-intercept? Y-intercept at 0, 8. So I'm going to say that's 8. Okay. Okay, there we go. State the polynomial in factored form. So factored form, well, I know, if you remember from our work, when it's in factored form, the zeros have something to do with our factors. So I'm going to do f of x equals, I'm going to leave a space here because I'm going to put that a value in. X minus 4, that means x plus 4 is one of my factors. x minus 1, that means x equals negative 1. That means x plus 1 is one of my factors, and likewise x minus 2. The lead coefficient is negative. If you remember lead coefficient being negative, what does that do to a quadratic function or parabola? So when it's negative, a equals negative 1, you know it's flipped, right? So I'm going to put a negative 1 over there, all right? So that just transfers over to there. Okay, circle the correct alternative. The left arm of the graph is rising. So here's a little bit of terminology. When I say rising, is ask this question of yourself: which way is arrow pointing? Up, so it's rising. The right arm of the graph is, well, it's pointing down, so it's falling. The degree of the polynomial is, well, it's a third degree, so it is odd. Third degree. The leading coefficient of the function is, well, that is negative. You can see the negative sign here, negative. Okay, letter B. Consider the polynomial function g of x equals x cubed plus 3x squared minus 6x minus 8. Identify the differences and similarities with f of x. So let's write these together. F of x equals, let me factor out that negative 1. And then here's g of x. And let's compare. How are they different? LC, lead coefficient. Constant terms are different. And then n behavior. How do we know n behavior is different? Well, I have a lead coefficient of negative 1. I have a positive 1. That makes our, we'll see later in a couple of examples, that makes our n behavior different. Okay, so n behavior meaning, does it do this and this, or does it do this and this, right? Where does it start? Where does it end? Okay, how are they the same? The degrees are the same, both third degree, and the x-intercepts are same. So if you graph these two and overlay them side by side, or sorry, if you overlay them, they'll have the same x-intercepts, but they'll start and end in different places. Okay, next page. Characteristics of polynomial functions. Okay, let's go through each of these. I'm going to do one for odd degree polynomial functions, odd degree, and then one for even degree below. So graphs of odd degree polynomial functions. The characteristics, odd degree, so degree 1, degree 3, degree 5, on and on, right? Extend from quadrant 3 to quadrant 1. When the lead coefficient is positive, it's similar to the graph of y equals x. So here's my trick, or my thing, on how to make this easy. So when you see when you see a cubic, so when you see a cubic, that's degree 3. When you see a quintic, when you see a degree 5, we won't see this septic. That's weird, isn't it? That's for 7 degree 7, I'm pretty sure. Yeah. Not like the sewage tank septic thing, but I'm going to look that up real quick. Just a second here. Yeah, it is. It just happens to be the same word as, I just looked it up on my phone. It just happens to be the same word as like the sewage tank, like a septic tank. Anyway, when you have a cubic of degree 3, quintic of degree 5, septic of degree 7, and so on, right? Odd number degree, right? It follows this general pattern, when the lead coefficient is positive, it's similar to the graph of y equals x. So look at this graph of y equals x. This is how I remember this, right? This is to determine the characteristics of the end behaviors. The graph of y equals x, right, starts in quadrant 3, ends in quadrant 1. It does that. Notice the graph of the cubic starts in quadrant 3, does this little S-shaped thing, ends in quadrant 1. If you were to graph a quintic with a positive lead coefficient, it would have the same end behavior characteristics. So this is how I like to remember it, in that I just think about y equals x for a leading coefficient with an odd degree polynomial function. Comparing it to a graph of y equals x helps me understand what is the end behavior. Where does it start? Where does it end? Next example. Graphs of odd degree polynomial functions extend from quadrant 2 to quadrant 4 when the lead coefficient is negative this time, similar to the graph of y equals negative x. So similar to what I just did, if I think about the graph of y equals negative x, it starts in quadrant 2, ends in quadrant 4. Well, what does a cubic function, so also odd degree, but a negative lead coefficient, it starts in quadrant 2, does this little S-shaped thing, it ends up in quadrant 4. Okay, so when I try to think about a cubic, a quintic, a septic function, it follows the same end behavior characteristics as, let's say, like its close cousin or sister or brother, y equals negative x, because they are both, so y equals negative x, a cubic function, a quintic function, a septic function with a lead negative coefficient, a lead coefficient that is negative. They are all related in that they have the same end behavior. So that's the trick to understanding how that works. Okay. Let's go to the next part, which is graphs of even degree polynomial functions. So I'll show you another easier way to remember this, because now when we get into degree 4, so we're quartic, that's degree 4. I should mention quadratic, that's degree 2. Degree 6 is sextic. Octic is degree 8. Okay, you don't have to know those, but just giving you the names. Graphs of even degree polynomial functions open upward and extend from quadrant 2 to quadrant 1 when the leading coefficient is positive, similar to the graph of y equals x squared. So I use y equals x squared because we used the quadratic function. We studied quadratic function all of the entire course in Math 20-1, right? So we're familiar with what a quadratic does. Quadratic function looks like a U shape, right? Or a smiley face, opens up or down. In this case, when the lead coefficient is positive, it opens up. It starts in quadrant 2, ends in quadrant 1. Similarly, a quartic function here, positive lead coefficient, starts in quadrant 2, does this little, like this weird W-shaped thing, and look at that, ends in quadrant 1. Just like its close cousin y equals x squared, they're both even degree polynomial functions. They have the same end behavior, start and end in the same quadrants. Okay? All right, next one. Even degree polynomial functions open downward and extend from quadrant 3 to quadrant 4 when the leading coefficient this time is negative. So the leading coefficient here for this quartic is negative, similar to its close cousin y equals negative x squared. So a quadratic that opens down because the lead coefficient is negative. So these are even degree polynomial functions. Here's our quadratic. Okay, opens downward because a negative lead coefficient, starts in quadrant 3, ends in quadrant 4. Well, what does its cousin, the quartic function, do? Starts in quadrant 3, does this little, now it's not a W, but it's like this weird M-shaped thing, or we got peaks and valleys, and then it ends in quadrant 4. So this quartic function has the same end behavior as its close cousin y equals negative x squared, because they are both negative lead coefficients, and more importantly, they're both even degree polynomial functions. Oh, I'm going to back up. I forgot to mention some of this other stuff. Let's go back to graphs of odd degree polynomial functions. Have at least one x-intercept to a maximum of n intercepts. So if it's a cubic, it'll have a maximum of 3 x-intercepts. Y-intercept of a of 0, the constant term of the function. And a domain where it's all real numbers and the range is all real numbers. Okay, it has no max or min value. So if you take a look, right, this is not a max, this is not a min, right? Remember, the function keeps going negative infinity, positive infinity, so there's no min or max. Likewise with y equals x, there's no max or min. It just keeps stretching on and on this way and that way. Okay, characteristics of even degree polynomial functions have from 0 to a maximum of n x-intercepts. So for a quartic, a max of 4 x-intercepts. Have a y-intercept a equals 0, the constant term of the function, has a domain of all real numbers x. So you can see it stretches left and right. And the range depends on the maximum or minimum value of the function. So in this case, so here, that's a min. Here, that's a max. Okay, and then think about it similarly to a quadratic function. If it has a maximum value, the quadratic opens down, right? If it's a minimum value, quadratic opens up. Same analogy for the even degree polynomial functions. Okay, next page. Okay, now we have a nice chart form. Let's continue our discussion and kind of solidify a lot of the characteristics we're seeing here. Identify the following characteristics of the graph of each polynomial function in the table below. So let's go to here. The type of function and whether it is an even or odd degree. So this is a cubic. This is odd degree, 3. Okay, this is a quartic. This is an even degree, and the degree is 4. This is a quintic. This is an odd degree, and the degree is 5. And this last one is quartic again. This is an even degree, and the degree is 4. All right, let's talk about the end behavior of the graph of the function. So end behavior for an odd degree, I'm going to compare, spelling, compared to y equals x, because that's a positive LC. Okay, lead coefficient. Okay, so what does y equals x do? Well, so when we do end behavior, I look at my LC. LC is positive, lead coefficient is positive. Okay, I think about y equals x. So y equals x looks like this. So therefore my y equals x looks like that. Therefore my cubic function, it's going to start in quadrant 3 and end in quadrant 1. So how do I like to show this? I'm going to get rid of that blue line, sorry. That was just for your reference here. Okay, so it starts in quadrant 3. So this is how I like to show it. Quadrant 3. and then I'll just do an arrow like this. I don't know what it looks like in between, and then it ends in quadrant 1, much like our y equals x. Okay, what about a quartic function? So I'm going to compare it. LC, the coefficient is negative. Okay, so I'm going to compare it to y equals negative x squared. So what we know about negative x squared is that it opens down, right? So I'm going to do my arrows like this. Imagine a parabola that opens down like that. Okay, but we're just going to do the arrows like this. It starts in quadrant 3, ends in quadrant 4. Okay, LC is negative. This one, LC is positive. Okay, and then that's all I want you to show for end behavior. Compare it to its cousin graphs, right? Quintic, odd degree. LC is negative, right? So quintic, I'm going to compare. This is an odd degree, so I'm going to compare it to y equals negative x. Remember our odd degree cousin, okay? So we know y equals x does this thing, right? Okay, if we draw that y equals x, it does that. Okay, so it starts in quadrant 2, it ends in quadrant 4. Okay, and the LC is negative. Quartic, even degree. This time the LC is positive, lead coefficient's positive. Okay, what am I going to compare this to? Compare it to y equals x squared, since the LC is positive. Okay, so this one, I know I have a parabola that does something like that, but I'm going to leave the middle blank because I don't know what it exactly looks like. It starts in quadrant 2, ends in quadrant 1. Okay, so imagine a parabola like that. Okay, and this one, the LC is positive. Next one, possible number of x-intercepts. So remember, by the definition, it's a cubic function. So I have 1, 2, or 3, and we'll show you why. Hey, shouldn't a cubic function have 3 all the time? No. Remember a quadratic? Remember when we did quadratics last year all through Math 20-1? Remember there were cases when there were 2 zeros, 1 zero, or no zeros, right? So likewise, a cubic function can have 1, 2, or 3 zeros, okay? But it can't have 0 zeros, right? For a quartic function, even degree, 0, 1, 2, 3, or 4. Quintic function, 1, 2, 3, 4, or 5 x-intercepts. And then quartic again, 0, 1, 2, 3, or 4 x-intercepts. The y-intercept, if I plug in f of x, y-intercept, f of 0, what do I get? Well, I get 2. G of 0, this one, I get negative 6. And likewise, you see, so h of 0, I get 1. H of 0, I get 1. And then p of 0, I get 16. Okay, that's the y-intercept, whether the graph has a maximum or minimum value. So remember, for cubic functions, it has neither a max or a min. For an even degree function, this one has a negative lead coefficient, so this is going to have a maximum. Again, odd degree function here, 5, degree of 5, there is no max or min. And then for an even degree function, a quartic, this one has a positive lead coefficient. So think of a quadratic with a positive lead coefficient. It opens up. So this is going to have a minimum value. Okay, let's match it to the graphs. First off, let's see here. Let's match these by n behavior first. Let's see if we can do this. Okay, I'm going to do the quintic one first because the n behavior, it starts in quadrant 2, ends in quadrant 4. Well, this is the only one that starts in quadrant 2 and ends in quadrant 4. Right here. Okay, so this is A. Okay, next one. Again, I'm going to do n behavior. Cubic, this one starts in quadrant 3, ends in quadrant 1. Starts in quadrant 3, ends in quadrant 1, so D has to be our cubic function there. Okay, and then the last ones. This one, the n behavior, quadrant 3, quadrant 4, starts and ends in quadrant 3 and quadrant 4 for our quartic function. This is the one that matches, so our quartic function, the first quartic function here, it's an even degree. It opens down, right? So this one, we can see it opens down. So that has to be B, and then the remaining one is C, but let's see why it's C. We see that it starts in quadrant, oops, right here, starts in quadrant 2, ends in quadrant 1, it opens upward. Starts in quadrant 2, ends in quadrant 1, opens upward. Okay, so that has to be that final quartic function. All right, next page. Okay, example 3. Let's do an application. A skateboard manufacturer determines that its profit P in dollars can be modeled by the function P of x equals 1000x plus 1.25x to the fourth minus 3200, where x represents a number in hundreds of skateboards sold. So remember that. State the degree of the function P of x. So I'm going to write it in descending order. So 1.25 x to the fourth plus 1000 x minus 3200. Degree is 4. Identify the leading coefficient and the constant of this function. So leading coefficient is 1.25 and the constant function. So how do we get the constant function? It's right here, right? It's when P of 0 equals 1.25 0 to the fourth plus 1000, 0 minus 3200. Simplify all that. We'll get a constant term of negative 3200. Does that make sense? When you sell 0 skateboards, your profit is negative 3200. Well, negative means this is a loss. You're not making money, okay? Describe the end behavior of the graph of this function. Well, it is quartic. LC is positive. So quartic, even degree. I'm going to compare y equals x squared, right? We know how that behaves. It opens up, so starts quadrant 2, ends quadrant 1. So off to the side, oops. Starts quadrant 1, sorry, starts quadrant 2, ends quadrant 1, okay? Next one. State the restrictions on the domain of this function justify your choice. Well, now we have an application, right? It's not just a function, it's an application, so it's real world. X, our number of skateboards, must be greater than or equal to 0 because can't sell negative number of skateboards. Okay, that's one restriction. Okay, and then X must be an element of whole numbers. Okay, Y, number of skateboards is discrete, right? Remember from grade 10 math, discrete versus continuous. Discrete, so 0, 1, 2. So can't sell, or I can't have 1.5 skateboards, right? Explain what the x-intercepts of the graph represent in this context. X-intercept is where P of X, the profit, is 0. This is the break-even point. So break-even point means no loss, no profit. This is where the money you're making, it covers exactly your expenses. So you're breaking even, okay? Determine the profit from the sale of 1,200 skateboards. For 1,200, use x equals 12 because, remember, the number is in hundreds. So it's 1,200, so I have to use 12 in the equation. So the profit, P of 12, equals 1,000 times 12 plus 1.25 times 12 to the fourth minus 3,200. Profit is 34,720. I'm going to challenge you to try this on your calculator. Not required for this lesson, but graph it. Not going to do it for you, but use the window. And then, and then see what you get. Okay.